Hello, everyone. Welcome back to the AAS YouTube channel, and this is more of the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Fritz Benedict with us today. Hi, Fritz.
Hey, how you doing, Frank?
I'm doing well today on this, my early morning.
Well, it's mid-morning to me.
Very good. So where are you at?
Austin, Texas.
Austin, and we are in late August 2020 in Austin. And is the humidity up or down?
It's up. Temperature's down. Last week we had 108 several days, and today it's only in the 90s, but the humidity's up because the flow's off the Gulf again. So it's like our monsoon, I guess.
Mm-hmm. Yeah, we get the same. I'm in Phoenix, and we get the same sort of Gulf phenomena this time of year. So this is also our monsoon season. And that's a lovely, is that really your bookcase behind you?
Yeah, it's my actual bookcase. And unfortunately, I'm not actually in that room. So that's a fake backdrop. But the Wi-Fi reception in that room is so terrible, we couldn't do an interview. So I said, well, I still want to brag about my books. So cool. There they are.
You see some awesome pictures of some telescopes, probably in McDonald, I would guess.
Yep, that's McDonald.
That's really cool. So what do you like to do for research?
I do astrometry.
Okay.
And that's a word that puts people to sleep usually, but there's a lot of good stuff come from astrometry. I got in the game many years ago using a machine called a PDS machine to scan plates, back when we had actual photographic plates. And the project was to learn where the moons of Jupiter were well enough so that Voyager wouldn't crash into them as it went by.
Well, that's a good thing.
Yeah. So that's how I got my feet wet in that game. And then the Hubble Space Telescope came along. We needed a guide star system, and I knew how to do that. So we designed a conceptual guide star system for Hubble, and they ran with it and did the real one. But
very cool.
I stayed away from the nuts and bolts of that.
Mm-hmm.
Still doing astrometry, scientific astrometry.
Cool. And that will probably lead us to this lovely research notes. Let's go ahead and take a look at that research note. So I'm going to share my screen. And this is research notes of the AAS. A moving target, revising the mass of Proxima Centauri C. And Fritz, take it away.
All right. Well, this is actually the second in a series because we did the first one, I think got published the odd date of April 1st. And that one was just a mass for Proxima Centauri C. It turns out that back in the 90s, we used a significant amount of Hubble Space Telescope time to do astrometry of Proxima Centauri, looking for planets around Proxima Centauri. Okay. And we were unsuccessful in that. And basically, we decided that there wasn't anything that we could detect around Proxima Centauri. So our limits there were something like a little less than the mass of Jupiter, and the periods that we were looking through were less than 1,000 days. Okay. So that's where it stood in 1999 when that result got published in the Astronomical Journal. And I had a bottle of 25-year-old Springbank Scotch that I broke open to celebrate the fact that we actually made a decision, because for years we were getting data with this thing, and one week, yes, there was a planet there, and then the next week you'd get some more data and the planet would go away, and it was just driving me crazy. But finally, it was, the truth of the matter was we could not detect something. So the bottle got opened anyway, which was nice. So this brings us up to January of this year. And much to my delight, there was a paper by Damaso and his co-workers that purported to show a companion orbiting Proxima Centauri, which they called Proxima Centauri C. And this thing had about a 2,000-day orbit. And the way astrometry works, it's like a teeter-totter. So if you've got a planet orbiting a star, the planet and the star orbit a common center of mass. So if there's a planet there, the star is going to move a little bit. So if the planet's further away from the fulcrum, from the center of mass, the star is going to move even more.
Mm-hmm.
So this just, it's a little bit like when all you have is a hammer, every problem looks like a nail. Well, I had this astrometry that we never got a result out of, but we didn't know that there might be something there with a 2,000-day orbit.
Longer.
So I went back and reanalyzed the astrometry that we had, and now I had priors. I had priors, which is this knowledge of the possible existence of Proxima Centauri C.
Uh-huh.
And Damaso and his crew had some orbital elements that I could use as priors. And that includes, and so that's the leftmost column in that table called RV, and that was their result. So they got a 1900-day period. They got a time of periastron passage. They had a kind of a guess as to the eccentricity, but they had measurements of the amplitude of the variation, which was rather small. I mean, it's 1.2 meters per second, so that's very small. But they were priors, so I could go back to the astrometry and put those priors in and redo the analysis, now allowing for there to be an orbit. And bing, there was a variation. So that I published in the research notes on the 1st of April. That made me very happy, because I didn't want to go through the refereeing process. This was really old data that the only reason we could squeeze anything out of it is somebody maybe had a result, because the radial velocity people, they were a little iffy about it. I mean, it's very ratty data and a very small amplitude. So I said, well, it's probably worth doing the analysis and showing it in a research note. So I didn't want to make a big splash or anything. But then, as it happens in science, within about 2 weeks of that, there were some new results. And these new results, if you scroll back up, I can get to the reference there, is the Graton et al. Took a bunch of data with this device on the one of the large telescopes at the ESO, and that device is called Sphere, and it does direct measurements. So if there's a planet there that's of a certain brightness, then they have high contrast imaging, high resolution imaging, and they could actually measure the orbit of this object around Proxima Centauri. And they published that, and they had something like 9 measurements of the separation and position angle of what they thought might be Proxima Centauri C from Proxima. And the paper is a wonderful paper, and they spent literally half the paper trying to convince themselves that they weren't actually seeing what they were seeing. I mean, they were saying, this could be this could be that, this could be this, it might not be a planet. But then they published the position angles and the separations, and I took those and I did my analysis, sort of analysis we do with binary stars, and it's beautiful data. I mean, the orbit was fantastic, and I thought, this is ridiculous. I ought to be able to treat Proxima Centauri itself and this planet as a binary star system now.
Sure.
And we have plenty of history of doing that. I mean, we had a paper in the Astronomical Journal in 2016 where we did something like 11 or 12 M-dwarf binary systems to try to firm up the lower main sequence mass luminosity relationship. So if we have radial velocities and we have measurements of the primary star and we have measurements of the secondary, then we can do the same kind of analysis that we did in 2016. And so within weeks of publishing the first research note, I had these results that you see in front of you. And there we actually have, not only do we get the mass of the planet, but we get the mass of the primary as well. So it's actually helped firm up the mass of Proxima Centauri. And it's given us now, our original number for the mass of the planet was 18 plus or minus 5. Now it's 7 plus or minus 1. And it's still somewhat of a question, because the radial velocities were very ratty. The very fact that you can see this planet is a conundrum, as a matter of fact, because it should not. I mean, if it's 7 Earth masses, those are Earth masses, by the way. If it's 7 Earth masses, how big can it be? It can't be very large, right. And yet it apparently can be seen with this sphere equipment and one of the large telescopes at ESO. So you've got ratty RB, you've got old astrometry from Hubble Space Telescope, you have this new astrometry, which raises interesting questions about, is this real or not? And the other one is that my friend Pierre Cavallo has taken Gaia data, Gaia proper motions into Hipparcos proper motions, and done an analysis of the change of them over the past 20 years or so. And he can infer the existence of a planet around Proxima, and he gets basically the same mass that we've been getting. So all of these various avenues of investigation all end up with, yeah, there's probably a planet there, Proxima Centauri, and it's probably something like 10 Earth masses. And it's just been a great deal of fun to get value out of some data that sat on a series of hard drives over the past 20 years. And it's kind of miraculous that I can still go and find it.
Well, that's true too, given the technology change on how.
Yeah. No, it's hopped from one hard drive to another hard drive over the intervening years. But so that's the story now. And people, telephone's ringing. Just a second, let me.
I love it. We won't be listening in to Fritz's telephone call.
That I was going to give myself for either finding a planet around Proxima or not. So now that I've measured the mass of a planet around Proxima, it seems sensible to get another bottle of scotch. And I go online and I see that this stuff is now $900 a bottle. So I'm not going to.
Celebrate.
I will not be celebrating with that. Yeah, that's right.
Well, I'm sure there's some fun Kentucky something or Tennessee something.
Oh yeah, no, I've got a fairly good selection. There's a lot of very good scotches you can get for far less than that.
I bet. So where do we go from here? Now that we have a punitive mass, so where does the community go? Where do you go next on refining this?
I probably stand aside now because I've squeezed these data for all they're worth. And I wait with keen anticipation for Gaia's results, because Gaia will, in fact, well, there's two avenues of investigation. Neither one will I have anything to do with. The first is Gaia is going to do astrometry. It's doing astrometry. It is going to characterize the perturbation far better than we could do with Hubble Space Telescope. So it actually has a chance to see Proxima Centauri b, which is the 10-day orbital period planet orbiting Proxima. Okay. So it should see a little curly Q in the sky, which is due to both these planets, and it's going to characterize those perturbations very, very nicely. The second avenue is to get more radial velocities. So the radial velocity technique is improving over and over and over again. I mean, people are shooting for 50 centimeters a second kind of precision in radial velocities. If they get down to that and have enough data on Proxima, then it's going to truly give you a much better handle on the orbital characteristics of C and B. And so people are going to take the Gaia data, going to take the new radial velocity data, and they will in fact determine with far better precision the mass of B and C than I have. But I've had the enjoyment and the fun of demonstrating the utility of these older data that frankly, we did not look for something with a 2,000-day period. We might have seen it if we looked there, but we just didn't, because we had 2,100 days of data. So you just don't, as a discovery instrument for exoplanets, Hubble's been a dismal failure. But to characterize exoplanets, Hubble's been great. I mean, we've done that now for 5 or 6 or 7 systems, and this is just the latest one of those.
Very cool.
So, and I'm retired, and I keep trying to retire, but doing astronomy is too much fun. And I'm still actually working on data that we acquired back in 2008 and 2009 on a planetary system, Mu Era, which is a it's like, I guess it's got 4 or 5 planets orbiting it. And we have a paper that was submitted to the AJ, and the referee didn't like part of it, so we're in the process of revising that. But right now, it's like Scotty in Star Trek saying we're sucking mud, right? We're getting down to the bottom of the barrel as far as Hubble Space Telescope data. But it's been a wonderful trip and a wonderful ride, and
awesome.
It's just a lot of fun to have an avenue to publish things like this. I mean, the research notes are fantastic for this. I mean, it's something it's a result, but it's a result that will not stand, right? Because it will be improved. It has to be improved. But as a result, it was worth putting out there, if for nothing else, to encourage people to say, hey, Benedict got it wrong. Let's show him how wrong he got it. Right?
Of course. Well, Crystal and Todd will be very happy about hearing that comment about research notes. Yep, that's awesome. Fritz, I want to thank you so much for taking the time today to chat about your wonderful research note.
I'm sorry we got interrupted, but that's how it works sometimes. All righty.
All right, everyone. Thank you so much.
All right, thanks.
See you on the next one. Bye-bye.
Bye-bye.